to thank you for the introduction and thank you for giving me the opportunity to give this talk in person. This is joint talk is Thomas Jensen from INRIA, and this deals with the interpretation of higher order programs. So since we are in this event, I tried to find a specific example that you might all know. How does it work? This way. So maybe you've heard the story that involves a company of dwarfs that founded a magician, and this story also involves a ring, and this ring has a specific property. When you put it on, you become invisible. Okay? So if we model this in an imperative setting using a put ring function that goes from type unit to type unit, well, this put ring function modifies the state of the company so that in this case the hobbit becomes invisible. Okay, but this one also has another very interesting property. Can you guess which one? What has the answer? The rest of the company is left unchanged, and that's very important actually. Okay, this relation that says that the rest of the company doesn't change at all, this is what we call a frame condition in a verification setting. Okay, and this is usually described as a set of memory cells that are not modified by the execution of the program. But in this talk, we are not interested in the imperative setting, but rather in the functional setting. So in a functional setting, you can model a similar put ring function, but this time it goes from type company to type company. It takes as input a company and creates a new fresh company as output, where the habit passes okay. Okay. And in this setting, what I call a frame is the relation that holds between the input company and the output company. Okay. So this frame is so you can see it as a specification of your program. Okay. It describes both the parts that did not change between the input and the output, and how the parts that were modified actually changed. Okay. And these frames, this is what we're interested in this talk. So frames are input-output relations, and they are interesting because they provide very useful information. So if there are compiler writers in this room, well, you may be interested in knowing that a function call does not modify some parts of your state, because if you have this knowledge, you could implement very aggressive, let's say, commands of expression elimination. Okay. If you are more a program verifier or a program verification guy, then you would also be very interested in which part of your state did not change, because if you have a property that holds on that part of the state that did not change, then you know for sure and quite easily that this property still holds after the function call. Okay. One caveat is that these frames can be very large. Okay, so if you have to write them down manually, it's a daunting task. It's also quite difficult to maintain when your program evolves. And the proofs are rather uninteresting to do, but still very long. Okay, so we had this idea, Thomas and I, that maybe we could infer these relations in an automatic manner using abstract interpretation techniques. And in this talk, we will focus on the case of higher order functional programs. So it's not the first time that we focus on that question. So 3 years ago at Purple, we presented the case of analyzing a first order program written in a first order language. Okay. At that time, we introduced a specific abstract domain that is called correlations that describe relations between the values of algebraic data types. And we applied this to the verification of an industrial microkernel OS, where we showed that using these techniques, you could discharge automatically 2/3 of the preservation lemmas that you had to prove. So definitely, this information, these frames are extremely useful in practice. More recently, we have extended this work to handle programs that perform also arithmetical operations, so that we could infer frames that involve numeric constraints between the input and the output. And you might have seen Santiago's talk on Monday at SAS that was specifically about that topic. Okay, but today we focus on higher order languages. So why that? It's not only a very interesting theoretical exercise, it has very practical applications in practice for real. So if you want, for instance, to analyze library codes or monadic code, well, you need to handle higher order programs. You have no other choice. Okay, so this work is a first step in that direction. So the contribution of this work, and which is also the outline of this talk, is as follows. We basically we follow very closely the abstract interpretation provided, the methodology provided by the abstract interpretation framework. So let me remind you what this is if you are not familiar with this. First, we define what property we're interested in. So in this work, the property is these relations between input and output, okay, for lambda terms. To this end, we introduce a notion of what we call stable relations. I come to that later. In the second step, starting from this property of interest, you define what we call a collecting semantics. Okay, so in this work, it takes the form of a denotation function that interprets lambda terms as stable relations between input and output. And we have proved that this denotation is actually sound and complete with respect to the property of interest. In the paper, you will also find other things like the equivalent definition of this denotation as in the form of a program logic. And the third and final step of this methodology is to perform a series of abstractions. Okay? At the end of this series of abstractions, you obtain an effective analysis. In this case, we have defined a modular analysis that is quite expressive, and we were surprised by this. And to do this, we had to extend the abstract domain the correlation abstract domain that we devised 2 years ago, so that it supports first-class functions. Okay, so that's good. And yeah, all these results have been formalized in the curve process steps. Okay, so input-output relations. So the programs we are dealing with are the untyped lambda terms. Okay, lambda calculus that is extended with sums and binary sums and pairs. This is really the textbook definition. There is no surprise here. We use the standard core by-value semantics for it. That is based on the substitution. It's based on substitution, and I've showed you the derivation of here. So no surprise here. Nothing new. The property of interest, as I told you, is relations between inputs and outputs. So the question is, what are the inputs of a program? Well, the inputs of my programs are the values that I give for the free variables of my program. Okay. So here it takes the form of a value substitutions. That is a finite mapping from the free variables of my programs to values. So these are my inputs. Then we could use a standard reachability semantics for it. That says, given a set of inputs, a set of substitutions, which are the values that will be produced. Okay, this is what is traditionally used in static analysis, including control flow analysis that are specialized for higher order programs. But this is not what we are going to use today. We are going to use a finer semantics that keeps the relation between inputs and outputs. Okay, so given a set of inputs I, what are the pairs input-output that could be produced by another finite program? Okay, and this is used in what we call relational static analysis, or what some colleagues call transformation analysis. Okay. In the title, there was the word stable. So what is this thing? Well, it comes from the very simple remark that if you provide more inputs than a program needs, it doesn't matter at all. It won't change the results. Okay. So if here I define the extension ordering on substitutions, saying that sigma prime extends sigma when basically it defines more inputs than sigma. Okay. And we say that a relation is stable when it is stable under the extensions of the substitutions. Okay, so if I have a pair input output in my relation, then if I add more inputs but keep the same output, I still remain in that relation. So in a way, this notion of stability internalizes the property of weakening that you might know from logics or from type systems. And we explain in the paper that this is actually essential for the soundness of this work. And this notion should be also familiar to many of you, because if you are a logician, then it should remind you of the notion of persistence from the Euclid semantics. And if you are more a semanticist, then this is exactly a monotone function from the set of substitutions equipped with the extension ordering to the power set of values. So you shouldn't be surprised. I mean, you know this device already, in one way or another. Okay, so this is where it becomes a bit hotter. So let's start to interpret lambda terms as stable relations. So here we define a denotation for lambda terms. Okay, so it's this double bracket T that is defined in a compositional way in the T-real syntax of T, and that computes an input and information. It is indexed by an environment that maps variable to stable relations, and it produces as output, this is proof, that we prove that the output is also a stable relation. Okay. And what is interesting is that this denotation actually coincides with the semantics that I've showed you a few slides ago. Okay, so first, it is a correct over-approximation of that semantics, which is something that you absolutely need if you want to derive a correct static analysis. So here I am following the definition. So what does this theorem say? It says that if I take an input in the set of inputs that are admissible according to the environment E, and if I give these inputs to my program T and obtain a value V, then the pair sigma V is indeed in the denotation that I have just defined. Okay. What is also interesting is that we have completeness here. So the two semantics actually coincide, and this is remarkable because if we had used the standard reachable semantics, reachability semantics, we could not show completeness. So both properties, we have proved them using the Coq proof systems. So let me show you some details about how we define this interpretation. So again, we follow the standard methodology of abstract interpretation, which says that you should go with the semantic definition and rewrite and simplify. So here I take example of pairs. I have a pair of two programs, T1 and T2, and I look at its semantics. Okay, so the definition is the pair of inputs, outputs, sigma V, such that if I give the inputs to my program pair T1, T2, I obtain the value V. So by reasoning a bit, it means that V is necessarily a pair of values, V1, V2, and that T1 reduces to V1 and T2 reduces to V2. And then I recognize the semantics of T1 and the semantics of T2. So I have defined the semantic, I have shown that the semantics of the pair T1, T2 depends on the semantics of T1 and the T2. So I may as well introduce a combinator on relations to write that down. Okay, and this combinator, pair, is defined like this. It contains value substitutions as input and pairs of values as output, such that if I provide this input sigma to R1 and R2, then I get back two values, V1 and V2, and these are the values that should compose the output. Okay. So since this equation holds for the semantics, we just define interpretation so that this is also true. Okay? And throughout the paper, we use the same methodology. So this combinator, per R, you might have seen it in the Popper paper, where we used it already. And it actually comes from the theory of allegories that you may be familiar with. Let me spare you the details about another example. What you should remember is that in the paper, we define several other combinators on relations, and that these combinators form the basic blocks of the denotation that we define for interpreting lambda terms into stable relations. And they satisfy beautiful algebraic laws that we have proof correct in Coq. And these laws were actually used in the Popper 19 paper. So this provides a nice after-the-fact semantic justification of that. Okay, but I have told you, I have promised that this would be about high-order programs, and so far, no lambdas. Okay, so what about lambdas? So to interpret lambda terms, lambda x dot t, I won't give you all the semantic definitions, but this looks like this: gather of the environments intersected with self of lambda xt. And you can understand this as an abstract closure, where the left part describes the environment of that closure, and the right part is just the code of that closure. So this gives you the intentional behavior of the program. Okay? But you can abstract this to describe the extensional behavior of the program. So here I introduce yet another combinator on relations that looks like a dependent arrow type, where R is a precondition, and on the right-hand side, I have the first condition that is implied by the semantics of the body of the function. Okay, so what does it look like, this arrow type? Well, it's a relation that's composed of a pair of an input sigma and a function v, for which I will consider all the possible applications. Okay, so for every argument v1 and any outcome v2, I will make sure that if v1 is in the input relation, then v2 must be in the output relation. And very importantly, we do this not only for the input sigma, but for any extension of sigma. Okay, so this quantification over all the extensions of sigma, this is what makes this relation a stable relation. This is essential. As I told you already, stability ensures the correctness of this one. So if you are familiar with cookie-style vertical relations, well, this is very frustrating. So this rule describes the extensional behavior of functions, as I told you. And it also enables to define a modular analysis of functions. And this is what we're going to use in the last step, when we are going to abstract the connecting semantics. Okay, so we start with this denotation that we have just defined, which it is indexically defined. It is still incomplete, so it means that we have not lost any information yet. And since it is inductively defined, it will lead to a program analysis that is also inductively defined, which is very nice. Okay, so this denotation tells you how globally all the inputs of your program are related to the outputs. And in the first abstraction step, we use what we call what is called in the literature the independent attributes abstraction. So we turn this into a set of relations, of binary relations over values, that tell independently how each input is related to the output. I will give an example on the next slide. And finally, each of these RV, of these binary relations, we abstract them again using the correlation of subdomain that we have extended to support higher order values. And this is what gives us function summaries. Okay, what we get in the end is an analysis that is quite surprisingly precise. So here's an example. The combine function that takes two pairs x and y as arguments, and that returns the pair as output made of the first component of x and the second component of y. So if I look at the denotation of the body of combine, well, if I unfold all definition, I get this, which is exactly what I just told you. That is to say, the output value V is a pair, whose first component is the first component of X, and second component is the second component of Y. Then, after the first abstraction step, we get two relations, one for X, that says that relates the input X to the output value. So here it just says that X and the value have the same first component. Similarly for Y, it says that Y and the output value have the same second component. And during the last step of the abstractions, we replace these two binary relations by the combinators we have used. But this time, these are pieces of syntax. Okay, and in this case, it takes this form. Okay, so we implemented this analysis in Oclaro. This is a bottom-up analysis, completely modular. Functions are analyzed exactly once. For every function, you compute a summary that describes its extensional behavior. This is just an example to show that the technical device of stable relations form a useful framework for defining static analysis. Okay, the analysis was really not designed to compete with very precise analysis like control flow analysis, and really does not compete. But still, we were quite happy that although it is fully modular, it is quite precise. So here is an example where typically you need some context sensitivity in control flow analysis for this example to get precisely analyzed. So this example is basically you take the identity function, you apply it twice on two different arguments, and then you keep only one of the results. Very simple. So how does it work from the high-level point of view with our analysis? Well, we first compute a summary of the identity function. In this case, it is very precise. It says that it is a function whose return value is exactly its argument. Okay. And then we instantiate the first time this summary that tells us that y1 must be the first injection. Then we instantiate independently a second time the same summary. This tells us that y2 must be a second injection. And finally, we get as outcome what we had computed for y1, which is must be the first injection. So in this case, we are on par with one CFA, although there is no context sensitivity at all. Okay, so it's time to conclude. In this work, we have laid solid foundations for the relational analysis of higher-order programs. We have defined a sound and complete input-output relational semantics that is based on the notion of stable relations. We have derived an example analysis that is obtained by successive abstractions of this denotation. All the results are organized in Coq. They are available. You can also run the analysis in your browser by flashing this code. And in the future, we want to support more language features like exceptions. We would like to improve the precision to exploit numerous types of domains. And very importantly, I would love to give an answer to this question of, can we define a control flow analysis that is relational and compositional? And I think this is an important step in that direction. Thanks for the attention.
So, yeah, there's one question.
Did this analysis allow you to automatically prove more of the preservation lemmas in the microkernel from the previous?
I would love to be able to give you an answer. Unfortunately, when I was working on this verification of operating system, that was at the time when I was working in the industry. I don't work there anymore. I don't have access to the code, so I cannot test. I guess this we would get the same results, okay, because this piece of code was not using high-order functions at all.
Any other question? Well, I have some questions. So in this classic Shari-Repnueli paper of 91, he described two different ways to perform interprocedure analysis. You have the operational approach or call string approach, which is kind of what CFA does. And will you describe what you do as the kind of functional approach that he described, but applied to higher order programs?
Yeah, I think that's a fair description.
Okay. And so I was wondering if so you use a denotation, an alternative denotational semantics to perform your abstractions, and after that you perform, well, you explicitly lose some information by having these independent attributes. So I was wondering, what kind of information do you lose when you do that, and can it be recovered by some more precise abstractions than the one that you propose of independent attributes?
So maybe I could answer the question, what information do we actually lose?
Yeah.
Okay. And quite importantly, what doesn't work well is when you apply your code an unknown function. Okay, so typically if you look at the apply function lambda fx, f of x, if you look at this, you will get a function that returns stop. Why is that? Because in the body, because of the independent abstraction, the independent attribute abstraction, what you describe is a relation between f and the result, that f is unknown, and a relation between x and the result is unknown. So you have no information at all. Okay, so if you wanted to handle this precisely, I don't think you can get precise information using independent attributes. You would need to use a different abstraction there.
So something that will relate the two different unknowns, something like this?
Yeah.
Does it happen a lot in practice? Or?
Well, it really depends on the code you're writing, but yeah, basically this .NAP is one of them. So yeah, I guess it happens a lot. So how can we recover some precision? So either we use a different abstraction, or we could use a mix of the call string approach and the functional approach. So that if I want to analyze a first order function, then I compute a summary. But if it is higher order, then I could use some context sensitivity and analyze it once the unknown function is better known. That's one approach.
Right. Any other question? Okay.
So I think I'm missing a bit, but like you had this, so the relation that's relating inputs and outputs, does that change? Can you change that, or is that something that's fixed? So basically, okay, can you analyze different types of properties using the same approach, or is that approach good for specific types of properties?
Oh, you mean the relational semantics and something new? You could analyze other things like the paper that you presented at SAS using a similar approach, but in the case of shape analysis. So it's trying to relate the shape of the input memory with the shape of the output memory.
Okay, but I meant like what you just presented, is it just a matter of changing the abstraction relation or something like that, and then we could use the same machinery and tools, or is the property that you're relating between inputs and outputs kind of part of the tooling?
No, it's not part of the tooling. So the interpretation function that I defined is not parameterized by any property. Okay.
But then what stops us from proving like maybe not total function correctness, but maybe like some sort of full functional correctness properties. Like, what enforces you to abstract?
Nothing. So in the paper, we have defined a program logic that hopefully can allow you to do this, to try to prove programs. Okay. Here we are just abstracting because we want some kind of definition.
Okay. So
Because the goal was to define at the end a static analyzer.
Okay.
That's why.
Okay. Maybe a different way to ask the question. For what sorts of properties would you be able to have static analysis that doesn't require any manual inputs?
Well, for instance, such a static analysis I have in mind is that, let's say, I'm programming the purely functional subset of a kernel, and but still I use exceptions, and I want to make sure that no exception is raised. Okay. That could be one application.
Okay, so let's take the speaker again.